So, welcome to our Chemaraderie for today. My name is Terry Humphreys, I'm from Curtin University. I'm just here to give you some notes and a bit of an introduction. So, I'd like to start off acknowledging the traditional custodians of the land that we're meeting on here today, the Whadjuk Noongar people, and I wish to acknowledge their elders past, present and emerging. We're going to be here listening to Melissa Nabi, and she's going to be presenting on the mineralogy made easy. So Melissa started off as an analytical chemist in the mining industry and has seen the evolution of instruments for single element analysis through to high-speed core scanning for mineralogy. So Mineralogy Made Easy will outline some of the newer techniques that enable fast quantitative mineralogy, in particular outlining SEM and LIBS. So please welcome Melissa.
Thanks for the introduction and thanks for coming along this evening. Can I have a quick show of hands of who is actually in the mining minerals industry? I know Ian is. Oh, there's quite a few of you. Right. Okay, well that might mean that you're a little bit more interested in what I'm saying. I represent AXT. AXT is a company that has been around for about 31 years. We started off by refurbishing X-ray tubes or manufacturing X-ray tubes. And then we started diversifying into other analytical instrumentation. So we now represent 60 international, or 60 suppliers, most of them international, in 6 key market segments. So we divide the types of instruments that we've got into 6 different areas. So life science, nanotech, material science industry, geological sciences and mining resources. So it's like, why have we got 2 things that are related to minerals? Well, geological sciences tends to be the high-end university application of the technology, so cutting-edge technology, generally used for the micro and nanoscale, and mining resources is the rolling of that technology out into industry. And so I tend to be more on the mining and resources side, which is the application side to industry. We have sales and services centres in Sydney, Melbourne, Perth, Brisbane and Auckland. So these are some of the techniques that we have for the minerals industry. So most of the things that we do are for imaging and analysis, and there's a lot of ancillary services that go around it. So Rigaku, they were the first analytical technique that we started representing, so XRF and XRD mainly. They also do X-ray CT. SciAps, who do portable XRF and LIBS instruments. TestCam, who do scanning electron microscopes. Elemission, who do LIBS technology, so that's going to be the main focus of my talk, and CatMax, who do the fusion instruments. So I started the Automated Mineralogy Incubator with AXT 6 years ago, and the whole idea of this was to bring new technologies to industry. So with new technologies, it's a great little bit of gear, but quite often the application is not fit for purpose for industry. So universities buy an analytical instrument because it's new, you can publish papers on it, no one's published papers on it, but industry will buy they'll buy a technique, not an instrument. So they're interested in the application, what comes out at the other end. And so people dread getting emails from me because I'm always saying, can you do this to the software? Can you just give us this as a bit of an output? So in the process with the Automated Mineralogy Incubator, we've built up a world-leading mineralogical geometallurgical team. And so these 5 people here help with application development and training and implementation, because it's not just an instrument, it's the application that comes out. And so ideally, so all of these my colleagues here, they all started off life as a geologist and they specialised in mineralogy, and then from that they've gone into different things. So Rowena is a petrologist. Sophia and Victor and Jing are really into process mineralogy. Alejandro is a geologist into the geological applications of mineralogy. So we do application development with training and implementation, and we provide a pathway for the integration of these high-tech instruments into routine operation, as well as economic access to the instrument. So when we started off 6 years ago, the concept was very different to where we are now, and we've evolved with what industry has demanded and been interested in. So the topic of today's talk is Mineralogy Made Easy. Now you have to excuse me, I normally present to geologists, process metallurgists, and although they're very clever people, they're more interested into the outputs of it, not so much the way that the instruments work. And one of the classic characteristics of a chemist is that we tend to be instrument operators. We need to know the nitty-gritty of how the instruments work in order for our QA/QC of the products that come out of it. So industry is more interested in the applications of that rather than how it actually works. So a lot of you probably know more about the actual hardware and how the instruments work than me. So what I'm going to talk about is bulk mineralogy, XRD, high resolution scanning electron microscopy for automated mineralogy, and high throughput LIBS, also for automated mineralogy. There are other techniques out there for mineralogy, such as instruments that use infrared bonding, so Raman and FTIR. There's other ones that use spectroscopy or spectral reflectance characteristics, but these are the ones that I'm going to focus on. So traditional mineralogy, as used by a geologist or a gem expert, is done with a hand lens, and they define a mineral by lots of different things. So the colour of it, the feel of it, the texture, and the cleavage faces that they can see on the mineralogy. And that's been around forever. And also, not so much hand lenses, but the ancient Greeks discovered how to, the first microscopes, but they weren't microscopes, they were kind of like just lenses. And then optical microscopes came into being, from what I can gather, around the 1870s. And so these work on using different reflectivity or transmissivity of the light. And so the geologists have to make a thin section, put it in a microscope and do lots of fancy things to work out what it is. Mineralogy is very, very subjective. So it comes down to the person that's looking at it as to what name they give it. So what I'll do now is I'll detail the three different techniques, specifically focusing on the ones I mentioned earlier. So bulk mineralogy, XRD. So we represent Rigaku, who have a small benchtop instrument and also a big high throughput industrial instrument. XRD, what is it? It's an acronym. So I talk in lots and lots of acronyms. My husband says I sell acronyms, but XRD stands for X-ray diffraction. It's been around from the early 1900s, but the first commercial instruments were in about the 1950s. So the way that works is you shoot an X-ray at a material, and then the X-rays are diffracted within the material. So what's diffraction? So they're kind of like bent through the crystal lattice. And you end up with an X-ray pattern at the top. So the original XRD instruments, you'd have to move the goniometer of the instrument to detect the X-rays from point to point to point to point. So they were called 0D X-ray instruments. So over time, then you've got 1D X-ray instruments who will pick up a one-dimensional line of this X-ray diffraction pattern, and nowadays you've got 2D, two-dimensional detectors where you can actually, so in a perfect world, the XRD pattern is a perfect ring. Do I share a ring? But if you have large particle sizes or a preferred orientation, you end up with hotspots, so you don't end up with a perfect ring. Or if you want to record a reaction that's changing over time, if you have a two-dimensional detector, it starts off with one mineral phase and the crystalline diffraction pattern then phases. So it analyses materials that are crystalline. So you have to have crystallinity, you've got a crystal structure. So the crystallographic structure defines the diffraction pattern. Now, it's used to determine major and minor phases if the concentration of that phase is over 1%. So if you've got trace minerals, it won't detect it because it's below the detection limit of the instrument. And it defines crystal polymorphs. So if you've got two minerals that have got the same chemistry, they will have the same chemical formula but a different crystalline diffraction pattern. And so you can define the crystal polymorphs. And so if you have one mineral, so if you look here, you've got all these different colours. So if you've got gypsum, that's purple, and so you've got the crystalline diffraction pattern of gypsum. But in the real world of minerals, it's very rare that you have just one mineral phase. You have multiple mineral phases. And so you end up with a diffraction pattern from all the different mineral phases. And so XRD started off as a qualitative measurement. It will tell you what's there, and then came meat-built analysis, which sort of deconvolutes that mixed spectra, and then you can quantitatively, theoretically, work out what minerals are present. The advantages of XRD is that it's a very fast way of defining the minerals. And so I mentioned before that if you've got trace level mineralogy, it doesn't work it out. But in a mining operation, It's the gangue minerals, so the minerals that you don't want, that affect processing more than the actual commodity that you're trying to get out. So it's a very fast way of determining the gangue minerals. You can analyse hundreds of samples a day. It's a very simple sample prep process. All you have to do is pulverise, and then you actually have to micronise a little bit further to try and get everything down to hopefully less than 40 microns. So the ideal particle size for XID is meant to be 5 microns, but if you grind everything to 5 microns, you end up with so many amorphous phases that you can't analyse them. So industry typically will pulverise something down to less than 40 microns, and so a researcher will be in shock horror, you've got to be less than 10, but industry just doesn't go, they want to analyse hundreds of samples, and so less than 40 microns tends to give them what they want. And you can set up the automation of results for minerals analysis. So I was talking to Reg over there. Reg used to be at Leinster. So BHP, Leinster and Mount Keith are big clients of ours. They've got Rigaku instruments, those big ones, this big one that you see here, where they can analyse hundreds and hundreds of samples a day, because it's the gangue mineralogy that affects their processing more so than the actual commodity that they're after. One of the limitations or the disadvantages of the technique, so the detection limit's about 1%. You must have crystallinity, so they must be crystalline, not too finely pulverised. It's not the best on clays, because clays tend to be a little bit finer than 5 microns. It's very difficult to determine the elemental substitution within minerals. So a high-end researcher can work out by a little bit of a wavelength shift if you've got a solid series solution. But generally in industry you can't, and the quantification is not accurate. So, sorry, spelling mistake there. So even though the Rietveld analysis deconvolutes those spectra to determine how much of each mineral is there, it's not particularly accurate. So now comes high-resolution scanning electron microscopy for automated mineralogy. So this is a different technique that acquires the data in a different way, and it gives you a slightly different output. So this is an instrument that we have got in our automated mineralogy incubator. It's a Tescan Tima with a 100-sample autoloader. So scanning electron microscopy, what is it? What does that acronym stand for? So it's where you have an electron beam that scans across a sample. And so if you look at this image here, how do you generate that electron beam? So you've got an electron gun, shoots out electrons through a series of lenses. They get focused onto the sample, they interact with the sample, and then the signal is recorded by a detector. When you shoot a sample with an electron beam, you get quite a few different things that come off. So the original use, from what I can glean, for these scanning electron microscopes was using these secondary electrons. So it was in the realms of topography. So they had better resolution. You could see a smaller particle than looking down an optical microscope. So they mapped the surface of a sample. But the biggest use that we use them for is utilising the BSE electrons and the X-ray photons. So you can see they all come from a slightly different depth. So the secondary electrons are all very much from the surface. So they're the ones that are used for topography. So excuse me if those that know more about this than me if I'm getting it slightly wrong, but remember who my target audience normally is. So the backscattered electrons come from within this activation volume here. So the backscattered electrons give you the average atomic number of what you're analysing. So if you are analysing a mineral, each mineral has got a chemical formula, so it's got a set combination of chemicals, and if you add up all the electrons in that chemical formula, set combination of minerals, if you add up all the electrons in that mineral, it's an average number of electrons. So by looking at the BSE, it gives you the average density of what you're looking at. And so you can have more than one mineral with the same density, but it's using the density of that mineral to define one aspect of the mineralogy. The other photons that you get out of these, what's called X-rays, so every element has got its own characteristic X-rays that it emits, and so it looks at the backscatter electrons plus the elements that are there, and it infers the mineralogy from that. There's other things that come off as well when you bombard something with electrons. There's catoluminescence, Auger electrons, and they're all used by mainly university applications, not so much in industry because they're a little bit harder to figure out what to do with them. So for automated mineralogy, scanning electron microscopy, these high throughput techniques use the backscatter electrons for density and then the X-ray photons for elemental analysis. This type of technology came out of CSIRO about 30 years ago. And so in those days they were using any old scanning electron microscope, any old detectors, and then they were getting the data and processing it to come up with automated mineralogy. TestScan is now, so it was launched as a QEM scan. So in industry you hear of the QEM scan and the MLA. They were the first two techniques that were using it. So the MLA was a spin-off from QEM scan. And now there's about 5 different manufacturers out there who do it. So there's TestScan, Thermo, Zeiss. Oxford have got detectors that use this type of technique. So anyway, what is it? It's a high-resolution microanalysis. The mineralogy is inferred by the element chemistry as well as the density. The advantages are that it defines the elements in solid solution. So for example, lizardite, nickel and lizardite. So if you're processing nickel, you ideally want pentlandite or one of the nickel sulfide minerals, but you can get nickel that occurs in the non-sulfide minerals, which really messes up your processes. And it can analyse elements heavier than carbon. So this image here that you see changing, it's a photo of an actual image, and then it's the of the actual sample that's been analysed, and then you've got this false colour image that's coming over the top with quantitative mineralogy that's coming out of it. So this technique came from a void in other analytical techniques. There was nothing around that could scan a sample in high speed, and the applications in the day were for process metallurgy. So instead of doing point counting down a microscope, it was kind of like automated petrology. Lots of different ways of acquiring the data. So you can, the spacing in between points is called resolution. You can collect your backscatter electrons at exactly the same spacing as your X-ray photons. You end up with so the way the technique works is that you set the threshold where you say ignore everything less than a certain value, and then you start recording the spectra of whatever is above that. So this is a typical spectra that you'll get off. This is pyrite, so you've got the zinc and the sulfide peaks, and actually it's not pyrite, it's sphalerite. Sphalerite with a little bit of iron in it, so zinc sulfide is sphalerite. So typically, if you have a low resolution instrument, you can see zinc and sulfur and that zinc peak there really quite well. This iron peak, you'd start to doubt if it's really iron or if it's background noise. What the TestScan software does is that it sums similar spectra, and then that evens out the background noise. So you end up with a high count peak that looks like this, where if you're summing a noisy background, you expect the negatives to cancel out the positives, or the positives to build on each other. So you end up with a high count segment like that. Other ways of acquiring the data is to collect the BSC spectra is a very, very fast method. So in this particular example here, these two zones have got the same BSC spacing, and so you can actually just collect one point from in the middle, but then you run the risk of, what if you've got two minerals with the same density? By collecting one point in the middle, it's just whatever happens to be like that. Or there's another method called dot mapping, which you set the spacing for your BSC spectra at one thing, and then you also have a variable spacing of the X-rays on top. So it's a very fast method of doing it. So the reason why I'm showing this is originally the techniques did it like that. So if you want lots of detail, it's a really, really slow analysis. But if you want a fast analysis, you lose out on the detail. So this method here is a fast analysis, so you lose out on the detail, but there's other methods that are in between. So what are the applications of this? Why do people do this kind of analysis? So this is a sample of 3 minerals that have lithium in them, or associated with the lithium industry. So you've got 2 spodumines here. So this is a digital photo of the sample that's analysed. So you've got pink spodumine, manganese makes it pink, manganese solid series substitution. Green spodumine's got iron, got lepidolite, purple lepidolite with albite. You look at it, you think, oh yeah, there's a little bit of different colour there, but what do those different colours actually mean? So when you zoom right in, you can actually see all the element maps within the sample. So scanning electron microscopy doesn't analyse an element with an atomic number lower than carbon. Even then, carbon is quite challenging. So it's not analysing lithium. It's determining these lithium minerals by the density and the ratio of all the other elements in that mineral. And so to validate this, another analytical technique, so laser ablation ICP-MS, was used, where you zap something with a laser and then it sucks atoms from the plasma into a mass spectrometer, and then using the mass spectrometer you can actually determine what the elements are. So this is a false colour image of the mineral map. You can see where the sodium is. So sodium you can say is a proxy for albite, but then you do further work and you see that it has actually got the chemical formula of albite. Magnesium, so phengitic muscovite. So for process metallurgy, it's really important for process metallurgists to know the particle size, so they know how much to grind the sample down. They also need to know the solid series substitution, so all the different elements that are within that mineral, because it affects their processing. Will it float or not float? It affects the purity of the final product. So we've got one customer who their main commodity is sphalerite. The person who they were selling the sphalerite to said, oh, you've got too much manganese in your sphalerite, you need to clean up your ore. And so by using the spectra, we were able to show that manganese is actually a solid series substitution within their ore. And so the mine then did a lot of further work, and they said, well, okay, the ore at the top is quite clean. As they go down further into their ore body, it's dirty ore. There's a lot of manganese in it. So it goes from being a high purity sphalerite to dirty sphalerite, because you can't get that manganese out of the ore. No matter what you do in processing, you'll never clean it out because it's part of the mineral. Other things that you can do, so this is rare earth elements. So when I was doing analytical chemistry in the early days, it was either gold or base metals or precious metals. Now we hear of these critical minerals, and so it's just another name for the same old thing. But critical minerals, two things that we never used to have interest in before are lithium minerals and rare earth minerals. So this is a 30 centimetre sample analysed by Chemo. You can see there's a lot of activity going on in there, and in this particular case it's chalcopyrite, finely distributed in the phengitic muscovite. Traces of brannerite associated with rutile and hematite, and the rare earth elements are mainly represented by xenotime. So you've got over here the backscatter image, iron, sulphur, and then segmentation of a false mineral map. So for a process, both for the geologist and the process mineralogist, it says a lot about their sample. So there's two very different applications for it. One is the geologists who want to know what's that mineral that they're looking at, what are the mineral associations, so the texture, and what's the grain size. And that information is equally important to the process metallurgist who's trying to design their plant and optimise their output. And so there's this field called geometallurgy, which is combining the geological nature of the materials with how they perform in a process operation. And so it's this little subset in the middle. So the mineralogical effects, the geological effects, and the metallurgical effects, how it actually works. If you look at this sample here, so if you do XRD, you grind your sample up, and you don't know the bulk mineralogy, you know how much is there, but you don't know how it's associated with each other. So looking at this sample here, sphalerite was the main commodity. There's pyrite and pyrrhotite, which affect processing. Quartz, you're trying to get rid of. So you can see the pyrrhotite here is this sort of greeny browny colour, but there's also finely interspersed pyrrhotite within the sphalerite, and so they would have to grind very, very, very fine to be able to get that out. To liberate the ore from the gangue as the first pass, it's quite a coarse grind, but to really get it out, the rest of it out, is a lot finer grind, and they probably wouldn't end up doing that. They'd probably just sell their concentrate as a lower quality product. And the SEM technique for process metallurgy, you end up looking at lots of tiny particles. And so some people go, well, why do I want to look at all these particles? But there's lots of statistics that go with the software where you can export the results as being how much of it is liberated, what's that term liberated mean, and how much is not liberated. And then you get recovery curves based on the liberation of it. So what is liberation? So this is some more examples. So liberated, most of the process operations, so there's gold and there's everything else. And so we operate mainly on trying to float them. So to float things, you can separate the sulfides from the non-sulfides. So liberation means how much of that particle is on the surface so that it's going to be floated up to the top. And so if you look at these ones here, now these are fully liberated, so titanium oxide's red, fully liberated in that there's lots of titanium oxide on the surface to go up with the flotation reagents. These are what you call middling, in that only a little bit of them are on the surface, and these are locked, so all your the mineral of interest is actually locked inside something. And so we're analysing a polished cross-section, and so you can see exactly what's going on in the sample. So you've got XRD that gives you bulk mineralogy, gives you the crystallinity. It's a very fast method of analysis. These samples here require setting in resin, or if they're a large enough mineral sample, you don't need to set it in resin, but it's got to be a certain size. You polish it, carbon coat it, and put it in the scanning electron microscope instrument. But you get quantitative mineralogy, mineral chemistry, mineral associations, and texture. So depending on what you want. The software is designed for the process metallurgist. So you can see here, you've got lots of different minerals that contain, these three that contain copper, although this one's copper oxide, so it may actually be associated with a specific copper oxide mineral, but sometimes we can't actually determine what the exact mineral is, so we can just say what it is. And then the data is presented in a statistical form. So day one, you've got mainly chalcopyrite. Okay, so these are all the copper minerals. So we've got there's only one of these instruments in Australia on an operating mine site. The grade of their ore is always around 0.5%. So it's a bit too low for XRD. XRD they use for all their gangue mineralogy. And the lady who was operating it said to me one time that one of the board of directors came through and he said to her, "You really need to get your recovery up." And she said, "Well, what do you mean?" And he said, "Well, you're only getting 32% recovery of your copper." And she goes, "Yeah, but our main mineral is bornite, and bornite is, I think it's 33 or 34% copper. So we're getting 34% of the bornite out, and I think we're doing pretty good, thanks." So, by having this type of technique, you can actually work out exactly what your recoveries are. And now there's this new technique, which I think I'm going to be running over time. I'll whiz through. So it's using LIBS, so high throughput LIBS for automated mineralogy. We've actually just had this installed in our office today. We've got the Canadian manufacturers over this week who've installed it. It's the first commercial system in the world. So they've built one in their own factory, proven it up, and we're the Australian distributors for them. So LIBS, what is it? So I've been an analytical chemist for 34 years. I hadn't heard of LIBS until about 5 years ago. It's like, what's this acronym? LIBS stands for Laser-Induced Breakdown Spectroscopy. I'll go briefly through the history, how it acquires data, the data outputs, applications, and the instrumentation. So this is a sample of what's called jadarite. It's from Jadar in Croatia, Serbia, and it was analysed, this particular sample was analysed by the LIBS instrument, so it's a false colour image, and this image here is a spectra of spodumene. It goes from 220 to 930 actually. So what is it? It's an acronym, Laser-Induced Breakdown Spectroscopy. It can analyse, so it's a laser-based instrument, it can analyse all elements, but it's exceptionally sensitive to the elements on the left-hand side of the periodic table. So X-ray technologies exceptionally is best for elements below carbon. It's very difficult to analyse. You can analyse beryllium and you can get instruments that analyse boron, but there's no instrument out there that analyses lithium. So X-ray technology, you're least sensitive at the top of the periodic table, more sensitive as you go down. LIBS, you're more sensitive to the left-hand side. It's a near instant analysis, so it's the speed of light. Microanalysis, so can analyse wet, dry, solids and liquids, but you need different instruments. Microanalysis, so it's a very small spot size, a bit similar to scanning electron microscopy. Process analytical control ready, so the results can be beamed straight off to a computer system. And just from the sales point of view, it easily analyses some low atomic number elements that X-ray technology can't. If you compare LIBS to other analytical techniques, so you've got the analytical grain size down here, so it's about 0.1 nanometres up through to 1 centimetre. On the left-hand side, you've got the detection limit, and different colours indicate what type of information you get from an analysis. So if you look at LIBS, it pretty well sits in the middle. So it's saying that the resolution is in the order of 10 microns, so the analytical instruments are sort of 10 to 50 microns. It's got moderate sensitivity, so it's not as sensitive as laser ablation ICP-MS or TOF SIMS or dynamic SIMS, but it's more sensitive than other techniques, so SEM-EDS. There's a lot of other acronyms there which tend to only be used in the high-end university application. So the developmental timeline of LIBS is closely associated with the history and development of lasers. So lasers were conceptualised by Einstein in the 1950s. He didn't call them lasers, I think he called them masers. But the technology was patented in 1960 with a Nobel Prize awarded for laser technology in 1964. And so if you look at, so a laser is a parallel beam of light. So instead of light going in all directions, it's focused to go in just one direction and it's synchronous. So instead of that energy going everywhere, it goes into one particular point. So in our life, I'm older than quite a lot of you young ones over there, but you know, when CD players first came out in 1992, they were, you know, really amazing, and all that data was stored onto a little CD. People are now going back to LPs for, you know, they say there's better sound quality, but that was never the case when I first started listening to CDs. And their uses in society started getting more and more. So laser eye surgery, the mobile speed camera, the surveyor's theodolite. And then as lasers got more and more advanced, they can be used for a lot more powerful things like laser cutting, laser welding. Now you get these destructive energy systems that are made from lasers who can obliterate something from 20 kilometres away. So lasers have really improved in their technology. And likewise, the uses in LIBS instruments has improved as lasers have changed. So this was one of the first commercialised instruments. So they tended to remain in the realms of research and academia, so always trying to figure out what LIBS is capable of. This instrument was developed to analyse beryllium in soils. So that same big bulky thing there can now be done by a little handheld instrument. LIBS first came to the attention of the mining industry with the landing on Mars of the Mars rover in about 2012. So this is the Curiosity here. The Curiosity can fire a laser onto a sample 2 metres away. It's got 2 lasers, one that determines how far away it is to focus it, and the other one, it blasts it. It's got a little nuclear reactor in the back, and this data is being back to Earth. So the latest Mars rovers have got LIBS instruments on them as well, as well as other systems. Yeah, and so L-Emission launched this system in 2017, so it was a scanning instrument, so it can scan core, an on-belt analyzer in 2018, 2019 slurry LIBS, and this core scanner in 2023. So there's no other system out there like it in the world, and we've been working closely with them on their mineral library application. The way a LIBS system works, it starts off with a laser, typically neodymium YAG laser, 1064 nanometres. It goes through a series of lenses, optics and lenses, where it's focused onto the sample. So that laser beam starts off wide, and then it gets narrowed down, so all that energy goes onto the particular sample. It interacts with the surface of the sample, and you get a plasma. And so this plasma, what it interacts with jumps up into an excited electronic state. So a plasma is a combination of electrons, atoms, ions, and molecules, but you need the electrons all whizzing around to make a plasma. As elements return to their ground state, they emit photons. Photons go through an optical spectrometer. Every element's got its own characteristic wavelength, so similar to ICP-OES. So in ICP-OES, the chemist would choose one peak that doesn't have any interferences. Peak height corresponds to concentration. So every element's got its own characteristic wavelengths, and every mineral has got its own set of wavelengths. Some elements are more sensitive to Lib spectra than others, and it comes down to how easy, or the first ionisation energy, so how easy it is to give up an electron. So on the x-axis you see the atomic number, so lightest element to heaviest elements. On the y-axis you see the first ionisation energy. So we all know that group 1 and group 2 elements give up electrons really easily. They like to exist as +1 or +2. As you go to the halides and the noble gases, they don't like to give up electrons. So they have high ionisation energies. And you see here lithium, sodium, potassium, rhodium, they all have very sensitive Lib spectra. That means you can get a really, really low atomic number, low concentrations, because they love to give up an electron. By the time you get over to the halides, like fluorine, they don't like to exist in the +1 ionic state, so they prefer to be in the -1 ionic state, but you can actually get a Lib spectra as a molecular line. So for example, calcium fluoride, calcium's 2+, fluorine's 1-. You actually get a molecular line as CAF+. Yeah. So the elements on the left-hand side are really sensitive. This is some classic spectra. So looking at spodumene at the top, spodumene, lithium industry, can't analyse it by any other technique, so it's actually very good timing for this technology to come out because there's nothing else. Well, X-ray technology can't analyse for lithium. Yes, you've got ICP, OES and AAS, but you need to dissolve the sample. So you can see two very strong peaks for lithium. There's an oxygen peak. Going down here, you've got iron. Some elements have only got a few strong peaks, so lithium's got sort of 3 strong peaks. This is sodium doublet here. Iron has got lots. By the time you get down to the rare earths and uranium, they've got thousands, tens of thousands. So this is an example of the molecular line. So you're not actually getting fluoride, but there's this very distinct hump that you can see here. So Libs like SEM technology, or the L-emission Libs, uses the whole spectral fingerprint. So it's not just one peak line, it's that whole fingerprint. So X-ray technology, you're exciting the atoms right next to the nucleus, and they're quite shielded from the outer electron clouds as to what's going on around it. So if you do get mineral effects or matrix effects, it tends to be from density, dense packing density. Libs, the electrons are on the outside of the atom, and they're greatly influenced by what's around it. And so there's lots of things that go on with Libs. So you have the laser matter interaction, you have the matrix effects, and those matrix effects actually work in the favour of Libs for mineralogy, because a mineral is a matrix, and in a certain commodity, you have other minerals that are associated around it, and that can affect a lot in the Libs spectra. So Libs has never been classically used for quantitative chemistry because of those matrix effects. So you need a matrix match calibration. But in today's world of chemometrics, you can build up a huge chemometric calibration where you, instead of having like 3 or 10 standards, you can have 100 or 1,000 standards for this multivariate chemometric calibration. So high lithium, high iron, high lithium, low iron. So it's the right time for this type of technology because you've got all the hardware and processes around there. So classic lithium spectra. This is copper minerals. So you can see the copper peaks in blue, the iron peaks in blue. Chalcopyrite and bornite have got exactly the same elements but in different ratios, but you do have a different spectra. So you can see the bornite spectral fingerprint versus the this is just showing the bornite spectral fingerprint. This one, chalcopyrite fingerprint versus bornite fingerprint. So different ratios. So it's a very effective way to determine the mineral because of the sensitivity of the matrix. Now, it's not a primary technique, so you do need another technique to define it. So our mineralogists can, you know what commodity you're looking at. They know approximately what minerals might be there. They can often tell by visual identification, that old hand lens of what is it, and then you build the mineral library based on that. But quite often we use another analytical technique, such as an SEM technique, to define the mineral. Oh, this is an example of molecular banding, so very distinct lines. the way it works is the laser beam scans across the sample. So you can see here all the spectra changing. So it's a spotty sample. So every different spectra corresponds to a different mineral. So like SEM technology, so it rasters in a square, a field, a rectangle. So for every pixel, you've got the spatial coordinates of it, the wavelengths and the intensities. Software deconvolutes it element by element, and you end up with a multi-element image, a bit similar to SEM technology. And you get these heat maps, so again, similar to SEM technology. So where it's red, it's the most intense. Where it's black or dark, you have absolutely nothing. So it's an instant way of telling you the element association with each other without doing any mineralogy. One of the beauties of what Elomission do is they do this principal component analysis where it instantly combines light spectra with light spectra, and you get this unsupervised classification or pseudo-mineral map, because they're all areas of the same spectra. You apply a mineral library, and then you end up with supervised classification or quantitative mineralogy. So nominally it's a 50 micron spot size of the beam, so totally different order of magnitude to SEM technology. So typically the lowest you'd go with SEM is about half a micron because of that activation volume underneath it, even though the beam's a lot smaller. So you compare half a micron to 50 microns, it's 100 orders of magnitude bigger. You can space out those beams, and by spacing them out you get a faster analysis. And you can also vary the scanning time. So it'll analyse this one field first and then you space it out. So ideally set up for core. So what does the data look like at lower resolution? So this is a section of core 100 mils by 40 mils. Analysing it at the highest resolution took 21 minutes. By spacing it out, the analysis time gets a little faster. So 100 microns is 5 minutes, 250 microns 50 seconds, 500 microns 13 seconds. But what does that do to the data? These are peaks for silver. So you can see there's a lot of activity for silver that it's picked up at high resolution, but by the time you space it out to 500 micron resolution, you might well miss that silver. But an element is never there on its own, it's always associated with something else. So if you look at these, it's exactly the same sample. You can see a lot of activity down here where that silver was. So this is a 3-element map, copper, titanium, iron, another 3 elements, calcium, magnesium, silica, those 3 elements with aluminium thrown in, the mineralogy that's been applied, and then these are peak intensity lines for titanium, iron and copper. So the silver is associated with those. So the theory is that you do a very low resolution scan of your sample, and then so that it's really fast, and so you can get maximum data on all your drill core, and then you go back and do a high resolution scan in those areas of interest. Additionally, it's got a high resolution camera, so we're just about to embark on with a company that does image analysis. So if you scan just a very narrow band down the middle of your core, it populates the rest of the core with mineralogy by the high resolution image analysis. So the image analysis is in the same order of magnitude as the same resolution. This is a real-time example. So the data outputs are all digitally co-located. So you've got your high resolution photo here, your zinc heat map, lead heat map, copper, iron, and then a mineral map. So you've got the legend down here. And so most of the samples have got iron. So if you look at this one, it's quite active with iron. But then if you start looking at the element deportment, so the whole mineralogy, you can really see where the sphalerite is. So that's the zinc mineral. So in this particular case, the sphalerite had a bit of iron. Galena, lead sulfide, no iron, but you've got pyrite versus pyrrhotite. So those chemical formulas are very, very similar. But because of LIBS being sensitive to matrix effects, so you've got your main elemental peaks, but then there's a whole lot of noise on the baseline. So that noise on the baseline is molecular banding, and you've got atomic lines, ionic lines, and so sometimes it's, more often than not, it's very difficult to work out what that noise corresponds to. But when you're using that whole spectral fingerprint, then it uses that to easily identify the elements. And so even if you have a different ionic state of the element, that is sensitive in the LIBS spectra. You know, it's either a slight spectral shift or different peak heights or something like that. So what is a disadvantage for quantitative chemistry, so those matrix effects, is really fantastic for mineralogy, because then you can use it to define everything. This one here is, again, looking at sphalerite type of minerals, but from a mineral processing point of view, or even exploration geology. So these are the two digital photos. They both look a bit similar, very bland grey, but then you start doing the mineralogy. So in this case, you've got the sphalerite that's associated with pyrite, but over in this one, you've got your sphalerite that's associated with micas, so mica and biotite. So they're both micas, but very different end applications for process mineralogy, as well as the exploration geologist to work out what they're associated with. So it's a very fast way of scanning core. So it can analyse the sample, as long as the surface height is within 4 millimetres, you can zap it directly. For process mineralogy, you can really work out the texture. So this is an example of lithium. So you can see it's quite a large crystal of spodumene that's containing, okay, spodumene's the green here, containing lithium. Looking at this one, you can see the lithium distribution, but the lithium is actually finely dispersed with chloride. And so it looks like a large crystal of it, but it's not. It's actually a lot of small crystals. So processing dream, this one, processing nightmare. This is the lithium concentration, so it's summing it over the edge of the sample. Again, you can see large crystals of, in this case it's spodumene, versus fine crystals. And so when you are zapping an entire length of core, you can actually work out what your quantitative mineralogy is. So you can analyse whole core if the surface height is within 6 millimetres, half core up to 40 millimetres wide, pressed powders if you want an absolute quantitative analysis, or rock chips. So at the end of the day, there's no one technique for mineralogy that gives you all of the answers that you want. And so your choice of analytical technique comes down to what type of results are you looking for. Do you want bulk mineralogy? Do you want to know approximately what's there? Just a qualitative analysis of what mineral is there? Do you want to know the crystalline structure? Do you want to know the mineral chemistry? So process metallurgists want to know mineral chemistry. So one of my colleagues, new mineralogist who was mainly into petrology before, looking down microscopes, when she started learning the TIMA, she said, why are there so many different definitions of a mineral? Surely, of one mineral, surely you just need one. And so she had never worked in the process metallurgy environment, where the process mets want to know the exact mineral chemistry because it affects all their flotation. Do you want to know the grain size or the texture of it? So the texture, meaning the grain size and the associations, is that important to you? In that case, you'd want to do like an SEM or a LIBS technology. What's the size of the sample? Is it a small sample? Do you want a high resolution analysis? Or have you got thousands of metres of core that you want to know the mineralogy for? So there's lots of different techniques that are out there, and the first question you ask is, what are you going to do with the results? And then you determine the technique that you want from that. Thank you. Any questions? Any questions?
Chip trays compared to the cores, do they have to do anything different, like because of the interaction, like with the surfaces? Or?
So as long as the height is within 6 millimetres, it can analyse chip tray. So if the particles really need to be greater than 1 mil, ideally 2 mil, because if they're smaller than that, you get this laser matter interaction. And so that little plasma that forms is 10,000 degrees plus. Any air that's there will heat up and make the samples move, as well as the sample getting physically excited. So if the chips are larger, as in true chips, it will analyse them. So what we've found is that with the LIBS, we need to use another analytical technique to make the mineral library. Sometimes our mineralogists can infer it without doing something else by looking at it. Yep, it's this mineral, it's this commodity, or these are all the elements. But if you've got kind of like the one I showed you with chalcopyrite and bornite, same chemical formula, same peaks, there's no absolute sort of peak height corresponds to concentration, whereas because you've got the Zeiss mineralogic, that would have in the software, an absolute quantification of the peak heights, so you can work out what the formula is. Whereas LIBS, we're not at that stage yet, so we use another method to validate it. And then once you've built that mineral library, then you can just whip through everything. Yeah.
Sorry, so with LIBS, you do one spot, you do several laser firings on that spot, do you?
Different ways of doing it. So with our handheld instrument, that's used mainly for quantitative chemistry, you can drill down on the one sample. And so the handheld instrument, you can do up to, 20 or 30 different zaps on the one spot. We find for minerals 3 is adequate, and then it rasters over a 12-point area. So it's only a little handheld instrument. With this technique, you can do a cleaning shot, but we find that we don't tend to. I mean, if you had a very dusty material, you'd probably want to. But, yeah, we try and clean up the core first.
Does that change the mineralogy?
Yeah, it does. So when we first started looking at some lithium core, because we'd done a lot of SEM work, we had all this sodium and potassium in the spodumene. It's like, this is really weird. And then we just washed the core and then it all disappeared. So that core came from an area that had hypersaline water. And so the water that had dried on the sample was really messing up our mineralogy. Yeah, because it uses mineral chemistry.
The laser impact itself could change the mineralogy, the heat of the...
No. Well, not that we've seen.
And does it sputter? Does it limit...
Yeah, it forms a crater a bit like a volcano.
Yeah. And so that limits how far apart you...
Yeah, so we've found that if you do one zap, and there's a vacuum that sucks up the dust. And so if you don't have that vacuum, then yeah, you get dust everywhere, but it's a heap of vacuum that just sucks away. And that's right next to where it's being ablated. So it stops that from happening. Yeah, but with the, if you do one zap on the one spot repeatedly, you see this like a volcano crater around it. So that in that case would limit your spacing between points. Yeah.
I've got one more question. So at the beginning you was talking about the XRDs and the ones that Rigaku sell,
Mm-hmm.
and you sort of started mentioning about in situ analysis, and I was wondering, do Rigaku actually have a in situ XRD instrument that you can have for the laboratory these days?
What do you mean by in situ?
Oh, so we've got sort of like I think it's we saw one by Enel, and so it's just like a normal diffractometer, but you can actually put like an Anton Par furnace in.
Yeah.
there.
Yep. So your Enel has got a curve detector.
Yeah.
Yeah, that gets all of that diffraction pattern at the one time. So Rigaku haven't actually got that curve detector yet. So our 2D detector is a bit smaller in the surface area,
Yeah.
so you have to actually physically move it.
Yeah. Cool.
Yeah. So I was, we tendered on the Rigaku instrument when that tender came out, and yeah, the specific requirements were the in situ heating to get everything happening all at once.
Yeah. Yes.
Yeah.
I do all that stuff, and I can also try and keep it all working. Huh?
Oh.
Yes. Right. Yeah. If we don't have any more questions, let's thank Melissa.